Let's get started. Today, I have the pleasure of welcoming a man who truly needs little introduction. Josh Starmer, the founder of StatQuest, has become a household name in the world of statistics and data science education. With over 1 million subscribers on YouTube, Josh is known for his remarkable ability to take complex ideas and make them simple and accessible. Beyond being a gifted educator, Josh is also a talented musician. I want to thank Josh for sharing his time, expertise, and musical talents with all of us today, and to all of you for the curiosity that brought you here. Please join me in welcoming Josh Starmer.
Are you guys ready for a silly song?
Yeah.
Okay. Ready? 1 year ago, I came here and talk about Transformers. And here I am today, and we're gonna talk about them some more. You guys are incredibly good. Your applause. That was a silly song. Hello, so I'm Josh Starmer. Today we're gonna. You guys heard the introduction. I have to tell you who I am. Today we're gonna talk about Encoder-Only Transformers like BERT, and they're gonna be clearly explained. I'm really excited about this talk because, it's like I played around with. I guess I should just give you the talk instead of like why I'm really excited about it. But you play around with ChatGPT and you're like, oh, this is amazing. And you can do really cool things with it. And I have done really cool things with it. Including writing a cover letter for a things ago that I got offered, but I didn't take it. And so you can do really cool things with ChatGPT. But when I was working on this, I realized there's even cooler things you can do, and people don't really talk about them. So today we're going to talk about those cooler things. Okay, cool. So way back in 2017, the first transformer ever made, had one part called an encoder and a second part called a decoder. And the encoder and the decoder were connected to each other so that they could work together. This first transformer was based on something called a seek-to-seek or an encoder-decoder model. Encoder-decoder models were designed to translate text in one language, like English, into another language, like Spanish. For example, Squatch might say, "Pizza is great." And the encoder would crunch a lot of numbers to encode the input. And ultimately decode those numbers into a translation. La pizza es magnifico. However, it wasn't long after this first encoder-decoder transformer was published that people realized that both parts could work just fine on their own. And it turned out we could generate text, including translations of text, with just a decoder. And these models, which form the basis of ChatGPT, were named Decoder-Only Transformers. Likewise, models based entirely on the encoder started to be very useful on their own. And these models, which form the basis of BERT and many other models, were named Encoder-Only Transformers. If you're not familiar with BERT, don't worry, you're not alone. However, just know that it can be a useful encoder-only transformer. So we'll mention it a few times, but don't sweat it if you're not already familiar with it. That's kind of the point of this talk, by the way, is that a lot of people aren't familiar with it. I'm trying to raise awareness. However, over the years, the models based on the decoder-only transformer kind of stole the show. Pretty much everyone has used, or at least heard of, ChatGPT or Gemini, or any of the other countless decoder-only transformers out there. And I've had some super smart people who keep up with AI and everything ask me if people still use encoder-only transformers. So in this StatQuest, I want to dive deep into the encoder-only transformers so that we can understand their significant but understated power. And that means starting with a deep dive into the first thing a transformer does, which is to create word embeddings. Word embedding converts words, bits of words, and symbols, collectively called tokens, into words. We need to convert tokens into numbers because transformers are a type of neural network, and neural networks only operate on numbers. One super easy way to convert words into numbers is to just assign each word to a random number. For example, if Squash just ate a delicious pizza, they might say, "Pizza is great." And we could assign a random number to each word. Now, if Norm came along and said, "Pizza is awesome," then we could reuse the random numbers that we already assigned to pizza and is, and assign a new random number to awesome. In theory, this is fine. But it means that even though great and awesome mean similar things and are used in similar ways, they have very different numbers associated with them. And that means the neural network will probably need a lot more complexity and training, and that means time and money, because learning how to correctly process the word great won't help the neural network correctly use the word awesome. So it'd be nice if similar words that are used in similar ways could be given similar numbers. So that learning how to use one word will help learn how to use the other at the same time. And because the same words can be used in different contexts or made plural or used in some other way, it might be nice to assign each word more than one number so that the neural networks can easily adjust to different contexts. For example, the word great can be used in a positive way, like "pizza is great." And it can also be used in a negative or sarcastic way, like "my cell phone's broken." Great. And it would be nice if we had one number that could keep track of the positive ways that great is used, and a different number to keep track of the negative ways. "Hey Josh, deciding what words are similar and are used in similar contexts sounds like a lot of work. And using more than one number per word to account for different contexts sounds like even more work." Don't worry, Squatch. The good news is that we can get a relatively simple neural network to do all of the work for us. For example, let's imagine we have two phrases. "Pizza is great" and "pizza is awesome." I hope everyone had lunch before this. Otherwise, you're going to be starving. Okay, so the first thing we do is create inputs to a relatively simple neural network for each unique word. I'm sort of just diving into neural networks without really even knowing if you guys are familiar with their basic structures.
Yes.
Yeah. Okay, good. Okay, good. All right. We're just going to dive in. And I'll assume you're familiar with the basic structures, like inputs. That's not too complicated, is it? So we got "pizza is great and awesome." Then we create an output for each word. Then we connect all of the inputs to at least one activation functions. And in this example, connect the inputs to two activation functions. The number of activation functions determines how many numbers we will use to represent each word. If you're not familiar with activation functions, don't worry, it's just a mathematical function. And we learned about those in high school, right? F of x equals something, right? Function. Plug in x, do the math, we get a y-axis coordinate. Okay, so that's all that is. Okay, bam. In this case, since we have two activation functions, we'll end up with two numbers or word embeddings representing each word. Then we add weights to the connections from the inputs to the activation function. So excuse me. Yeah, bam. So we added our weights. Bam. These weights are initialized with random numbers. So right now they're not very useful. So this is the original scheme we had. It's just random numbers for each word. But we're going to improve on that in just a little bit. But the plan is to train them and thus change them using this data. Lastly, we connect the activation functions to the outputs using some boring details that we don't need to worry about. And if you want to worry about those details, fine. You can watch the video later. Okay, because we have one word embedding for each word going to the activation function on the top, and one word embedding for each word going to the activation function on the bottom, we can plot each word on a graph that has the top word embeddings on the x-axis and the bottom word embeddings on the y-axis. For example, the word pizza goes here because its top word embedding is negative 0.11 and its bottom word embedding is 0.10. Does that make sense? Okay. Likewise, the word is goes here, great goes here, and awesome goes here. Now, with this graph, we see that the words great and awesome are currently no more similar to each other than they are to any of the other words. However, because both words appear in the same context in the training data, we hope that training the network will make their word embeddings more similar. The idea is that we want each word in the training data to predict the next word. For example, we want the first word in each sentence, pizza, to predict the word that comes after it, is. And we want the word is to predict the words that come after it, great and awesome. So in order to see which word the network predicts should come after pizza, we put a 1 in the input for pizza, and we put zeros in all of the other inputs. Then we do the math with the randomly initialized parameters, and we end up predicting great because it has the largest output value, 0.45. Thus, with the randomly initialized parameters, the network does not correctly predict is, the word that comes after pizza. However, after we train the model and we train with backpropagation, we end up with these new word embeddings, and pizza correctly predicts is, and is correctly predicts great and awesome. And now when we graph the words with the new word embeddings, these are the trained word embeddings that we just trained with our training data, great and awesome cluster together. This result is great and awesome because great and awesome are similar words used in similar contexts. And they ended up with similar word embeddings. Damn. So far, we've seen the simplest way to create word embeddings. We used a simple network that we trained to predict the word that comes after the input. However, just predicting the next word doesn't give us a lot of context to determine the optimal word embeddings. In contrast, if we had a more complicated training data set with these bigger, longer sentences, then we would have more inputs and outputs for our neural network. And we could connect everything like we did before. But now, because we have more inputs and outputs and longer sentences in the training data, we can add more context to the training process. For example, we can use this entire phrase, the pizza came out, to predict the next word of. Does that make sense? Like before we were just using one word to predict the next word. And now we're using 4 words, the preceding 4 words, to predict the next word. So we've got more context for that next word. In other words, I got ahead of myself. In other words, instead of just using one word to predict the next, we can use the preceding 4 words to predict the next. Just so excited. Okay, increasing the context can help create better word embedding values. But I want to point out that the way we're doing things right now ignores word order. And because we are not currently keeping track of word order, any jumble is just as good as anything else. In other words, the pizza came out of would give us the same inputs and output as the jumbled up phrase, pizza out came the of. Does that make sense? Right? Because we just have ones for the input words, and those are the preceding 4 words and the inputs. And then we just have we're just looking at the output of the next word, of, right? So the word order, other than of, has to be at the end. Those first 4 words can be any jumble, and we'll still end up putting ones in those inputs. So it'd be nice if there were if there were some way to create word embedding values that also took word order into account. And that leads us to the part of a transformer that comes after the initial word embedding layer, called positional encoding. Positional encoding helps keep track of word order. For example, if Norm said, Squatch eats pizza, then Squatch might say, yum. In contrast, if Norm said, pizza eats Squatch, then Squatch might say, yikes. So these 2 phrases, Squatch eats pizza and pizza eats Squatch, use the exact same words, but have very different meanings. So keeping track of word order is super important, right? If we're really going to have a larger context in which we can create embedding values, understanding the word order is important. Or keeping track of the word order is important. There are a bunch of ways to implement positional encoding, but the details are out of the scope of this quest. But you can check out these videos later. Anyway, now that we know that positional encoding helps keep track of word order. However, it would be great if there was also a way of keeping track of the relationships among words. For example, if the input sentence was this, the pizza came out of the oven and it tasted good, then this word it could refer to pizza. Or potentially, it could refer to the word oven. Josh, I've heard of good tasting pizza, but never a good tasting oven. I know, Squatch. That's why it's important that the transformer correctly associates the word it with pizza. What was that?
No, I was just thinking about tasting ovens.
Yeah, nobody wants to do it, right? It's like nobody wants to lick the oven. Okay, and that leads us. I shouldn't say that. Actually, there's probably someone out there who does. Who knows? Maybe I baked something incredibly delicious in there. Like, wow, this is so good I could lick the oven.
That should be a saying.
That's right. That's right. It's like I could open a pizza, like Squatch's Pizza Hut. It would be like, tastes so good you'll lick the oven. Anyway, that leads us to the part of a transformer that comes after positional encoding, called attention. By the way, there's a really famous paper called Attention is All You Need. I don't know if you're familiar with it. That's a total lie, right? We need word embedding and we need positional encoding. That title of that paper completely baffles me. Why did they do that? It's confusing. Anyways, it's not all you need. You need these 3 things. And specifically in an encoder-only transformer, the type of attention we're going to use is called self-attention. And so we'll describe that later. Attention keeps track of the relationships among words. Going back to our example about pizza coming out of an oven, attention can help correctly associate the word it with the word pizza. Note, there are different types of attention, but encoder-only transformers only use this thing called self-attention, and so that's what we're going to focus on. In general terms, self-attention works by seeing how similar each word is to all of the words in the sentence, including itself. For example, self-attention calculates the similarity between the first word, the, and all of the words in the sentence, including itself. And self-attention calculates these similarities for every word in the sentence. Once the similarities are calculated, they are used to determine how the transformer encodes each word. For example, if you looked at a lot of sentences about pizza, and the word it was more commonly associated with pizza than oven, then the similarity score for pizza will cause it to have a larger impact on how the word it is encoded by the transformer. Bam. Now that we understand the ideas behind self-attention, we understand the ideas behind the three fundamental building blocks that make up an encoder-only transformer. Word embedding converts the input into numbers with the hope that those numbers are somewhat similar to each other. Excuse me, for similar words, right? We want similar words to kind of cluster to each other. Okay, positional encoding helps keep track of word order. And self-attention helps establish relationships among words. Combining all three layers creates a new kind of embedding for each token that takes position and relationships among words into account. And this new type of embedding is sometimes called context-aware embeddings or contextualized embeddings. And there's probably other words for it too, or names for it. But we're just going to use those for now. That's enough. For me, it is. Okay, because context-aware embeddings include information about the position of each word as well as the relationships among the words. Context-aware embeddings can help cluster similar sentences or even similar documents. Man. To summarize, encoder-only transformers like BERT that only use self-attention can create context-aware embeddings, and just like word embeddings can help cluster similar words that are used in similar ways, context-aware embeddings can help cluster similar sentences or similar documents. Note, the ability to cluster similar sentences and documents is the foundation for something called retrieval augmented generation, or RAG. RAG works. So, give you an example of it. You guys familiar with RAG? Everybody knows what it is. Okay, so I don't have to give an example. When I wrote my cover letter, I took my resume and the job description and all those things, and I just dropped it into some AI, and it said, write a cover letter based on these things, and it used RAG to do that, which is cool. Anyways, so RAG works by breaking a document into blocks of text and then using an encoder-only transformer to create context-aware embeddings for each one. So if we had a document about pizza, or food in general, I guess, we break that document into, it's a short document, it's only got 3 sentences. So we break it up into 3 sentences, and then we create the embeddings for those. Now, the thing is, you can download BERT, or you can download some encoder-only transformer from Hugging Face, and you can just, without even really pre-training it to a certain extent, you can just start generating these embeddings immediately. And so we could just, without having to train it, we could just generate these embeddings. It's great. And then when someone gives an AI a prompt like, what is pizza? RAG generates embeddings for that phrase, for that prompt. What is pizza? And then it finds the chunk of text that is most similar to the prompt, right? So it basically just measures the distance between what is pizza and all the things, and it goes, oh, I'm really close to pizza is awesome in this space, and then it returns that, and so then we say double bam. Okay, now that we understand the main ideas behind encoder-only transformers and context-aware embeddings, I'm going to talk about a couple of things that I think are really cool, very briefly. Yeah, I always get ahead of myself. We're going to talk about another cool thing we can do with them. This is something that and most people don't think about. Like the RAG thing is like, oh yeah, we're just going to do RAG, no big deal. This next thing hopefully will be a surprise. Okay, one thing we can do is use the context-aware embeddings as inputs to a normal neural network. A normal neural network. Let's try to say that 3 times fast. That classifies the sentiment of the input. For example, we might want to see if people are posting positive or negative sentiments about pizza on LinkedIn. So this is like an actual business case. Imagine you work for like Squatch's Pizza Hut and you were like, what are people saying about Squatch's Pizza Hut on some social media thing, right? But you don't want to like sift through it by hand. We could just scrape all that data and then start running it through our encoder-only transformer that creates the embeddings, which then can be used for classification. And so the context-aware embeddings that the encoder-only transformer creates are great inputs for a neural network that does that type of classification, right? So what we did is we took our encoder-only transformer and we just jammed a normal neural network on top of it that does classification. And it says, based on the inputs, people are either loving it or they're hating it, which are pretty extreme. There's probably people that are pretty neutral about Squatch's Pizza Hut. So we could have other options as well, but you get the idea, right? Yes. Okay, good. Okay, alternatively, this is the other thing I think blows my mind. Alternatively, we could use the context-aware embeddings as variables in a logistic regression that does that classification. So is everybody familiar with logistic regression, right? It's just like y equals this equation. Well, just think of these embeddings as those variables that we use for our logistic regression equation. And then we just fit the logistic regression to a handful of examples, and that's how we train the logistic regression. And then we can do like standard logistic regression on it. And what I think is really cool about that is logistic regression is super cheap and super easy to do, right? You can do logistic regression with relatively large data sets on basically your laptop. I mean, you can do a lot of transformer stuff nowadays on your laptop, but you know what I'm saying? Like, it's a very simple thing. It basically is free to do. There's no expense. And so if you're working at some company and you got a finite amount of budget, a finite amount of time, you can knock something out like this really quickly, and you press your manager, and they'd be like, "Wow, you're the best. We're going to give you a raise." Or maybe they'd be like, "We'll give you a snack." Like, I wanted a raise. Anyways, I love logistic regression because I have a channel called StatQuest, and stats are like my heart. That's like, I love stats. And so the fact that the old stuff is coming back, and this is the other thing, it's like people always ask me, like, do I need to learn these old things? And I'm like, yeah, because you can do stuff like this, and this is cool. And they're like, oh, I don't want to learn that. And I'm like, well, tough, you got to do it. Anyway, even the encoder-only transformers like ChatGPT get all of the hype. The context-aware embeddings that encoder-only transformers create can be used in a wide variety of settings to do very cool things. So we end on a triple bam. And before you get really excited and you're like run away, you're like, oh, he's done. I don't have to listen to him anymore. I do have bonus material. That was the coolest sound ever. Right? It was like, I heard, oh, I'm interested in the bonus material. Instead of, oh. That was really cool. So if you'll just wait a second, I'll get you the bonus material. This is super cool. I'm really excited. It's also kind of anyway. I'm not gonna ruin it. While you're at it, just escape the mess, and then pull up the other presentation. Back just a second. Yeah, you can stretch it. if you need to. USF has the easiest setup ever. Anywhere else, I guarantee you, anywhere else in the whole wide world, trust me. It would have taken like half an hour. We would have missed all of the bonus questions, bonus content. And it would have just been a total disaster. So this, you guys, this is a world premiere. I've never shown this to anyone ever. This is like my top secret. It's not even done. I don't even know what it is. I don't want to make a video out of this. This is just something I did over the holiday break, and I want to share it with you because I think it's interesting. I hope it's interesting. It's interesting to me. Maybe that's good enough, and you guys are going to sit through it. How can we have confidence in neural networks and AI? That's a question that has been plaguing me for a long time. Because I'm a statistician, right? And like when we do a linear regression or things like that, we get confidence bounds, we get confidence intervals, we get like standard errors. What's that? Yeah, mean squared error. We get all that stuff, right? And so I can look at the answer that I get out of a normal linear regression, and I'll be like, yeah, this is the number that it says, but it's also plus or minus these things, and I have a good sense of what that variation is, and that's the genius of statistics, right? Is it takes noise in the data and it says, hey, we can deal with that. We can quantify it and we can make it so that you can make good decisions. Like I can say, this is the estimate, but the variation around it is this much. And so it's probably a pretty good estimate. Or we could say, this is the estimate and the variation's like really wide. And then we'd say, maybe that's not such a good estimate, right? So isn't that cool? And ever since I started using neural networks, I was like, I like neural networks. They're cool. They do fancy things, right? But I want that standard error. I want some measure of reliability, of confidence, right? And I'm never getting it. And so I was thinking about this over the holiday break, and so this is something I did for fun. Okay, a long time ago, I wanted to create a StatQuest that explained how neural networks worked, and so I made a StatQuest on how neural networks work. So I created this simple data set about a drug that was designed to treat an illness. This was at the start of COVID. So I'll give you some context to when I made this one. Okay, and I imagined we have a drug with 3 different groups of people with 3 different doses. Right, we have a low dose, a medium dose, and a high dose. The low dose was not effective. This is all pretend, right? I'm just making this up because I wanted to illustrate something, right? But just imagine that the low dose was not effective. So we set that to 0 on the graph. In contrast, the medium dose was effective. So we set it to 1. And the high dose was also not effective. So we set it to 0. So the reason why I wanted this data set to be like this is we can't fit a linear regression to it, right? That'd be terrible. And we can't do a logistic regression to it either. That would be terrible, right? And so I came up with this data set because this is a good example of something neural networks does well. It can fit a shape to this. And I got ahead of myself, so I'll end up repeating myself a couple of times. Anyways, you see how lame the straight line is. Bam, lame. In contrast, neural networks are cool because they can fit squiggles to the data and they can also fit bent shapes. Or even bell-shaped curves. That's cool. And unlike the straight lines that we looked at, this bell-shaped curve fits the data perfectly. When we plug in dose equals 0, the curve correctly predicts that the drug will not be effective. And when we plug in dose equals 0.5, the curve correctly predicts that the drug will be effective. And lastly, if we plug in the dose, it's supposed to just be 1.0. This is how rough this is. Anyways, just imagine we plug in the high dose. The curve correctly predicts that the drug will not be effective. So given this data set, I created this super simple neural network and fit it to the data. However, instead of getting a nice bell-shaped curve like this, I got this green squiggle. Just looking at the green squiggle, we can see that even though it's not exactly the bell-shaped curve we might have wanted, it fits the data really well. In other words, the green squiggle touches all 3 data points. For example, if we plug in dose equals 0.5, then the output from the neural network is 1.0, and that's the correct value, and it corresponds to the y-axis coordinate on the green squiggle. And if the input is 1, then the output from the, is the correct corresponding y-axis coordinate 0.0. However, this bump was a little disturbing because I looked at it and I was like, where'd that bump come from? Because I don't have any data in that region. It means that when we plug in 0.3 in this neural network, then the output is the corresponding y-axis coordinate 1.7. And 1.7 is much higher than any of the data we originally used to train the neural network. So the highest value in the training data was just 1. So 1.7 is almost twice that. It's a big deal. And so that bump is actually much taller than I'm showing it on the curve. I just couldn't have difficulty drawing it. On the other hand, we only trained the neural network to create a shape that fit these 3 specific points. And since there were no data in these regions, there were no constraints on the shape that the neural network created in those regions. In other words, from the perspective of a neural network, this shape is acceptable because it touches all 3 points. Likewise, this shape, with this funky bend where there is no data, is also perfectly acceptable. And so is this shape. And while these 2 bumps might look strange, we just don't have any data in those regions to know if they are reasonable or not. In other words, because there are no data in these 2 regions, the output from the neural network in these regions amounts to a guess. And because there is no data in these regions, we don't know if the neural network is making a good guess or a bad one. So, based on the original green squiggle, I made a hypothesis. Given that the green squiggle represents guesses about drug effectiveness, I hypothesized that inputs that are relatively close to the original training data will result in relatively good guesses. And input values that are relatively far from the original training data will result in relatively bad guesses. In other words, I thought by measuring the distance from the input to the nearest training data, I could quantify how much confidence I should have in the neural network's output. For example, the x-axis coordinate for this input is relatively close to the x-axis coordinate for this point in the training data. So we might expect a good guess from the neural network. In contrast, the x-axis coordinate for this point is relatively far from the x-axis coordinates from the points in the training data. So we might expect a bad guess from the neural network. Okay, now I needed a way to test the hypothesis that the distance between an input and the training data is related to how good a guess a neural network makes. So I downloaded the MNIST dataset, and I can't remember what MNIST stands for. So I'm not going to tell you what it stands for because it's not that important. Just know it's a dataset full of numbers. The MNIST dataset consists of 60,000 labeled images of handwritten numbers. For example, the MNIST dataset gives us this image of a handwritten 0, and it also gives us the label that tells us that the image is 0. This means I can feed the image into a neural network and compare the output to the label to know if my network made the correct guess. Then I created a relatively simple neural network to classify the images. It consists of 784 inputs because each image is 28 pixels by 28 pixels and thus contains 784 pixels. In other words, we have 784 inputs, one for each pixel in the image. Then the inputs are then connected to a single hidden layer with 10 ReLU activation functions. So that's just a function that has a bend in it, which is connected to a softmax layer. And a softmax layer is just something that makes the output easy to interpret, which we connect to 10 outputs, one per number, 0 to 9. For example, when the input image was this specific handwritten number 2, then the black pixel in the upper left-hand corner had a value of 0. So we plugged a 0 into the first input. Then we plugged in the input values for all of the other pixels in the image. And after training, the output for the number 2 was 1. So that's a little confusing the way I said it. But the output is the number we're predicting, right? And we had a 1 there for 2. There's a 1 for 2. And that means we correctly classified that image. And everything else was 0, right? So we did it right. And then I said, bam. I did. I was just sitting there like, bam. Okay, in contrast, when the input image was this specific handwritten number, 2, which is a little sloppier, then the output for 2 was only 0.1. And the other outputs were all over the place, with the largest output going to 8. So in this case, the neural network misclassified the input image. Wah, wah. Okay, now because the MNIST dataset has 60,000 labeled images, I could use 50,000 labeled images to train the neural network, leaving me 10,000 images to test my hypothesis. In order to test my hypothesis, I ran an image that wasn't used for training through the neural network, kept track of whether or not it was correctly classified by comparing the images labeled to the output, and I measured the distances between the input image and all of the images I used to train in the neural network. Josh, how do we measure the distance between two images? Great question, Squatch. To understand how to measure the distance between two images, let's look at a super simple example. Imagine we had a super simple image that just had 2 pixels. Now, since both pixels are white, we'll give each one a value of 1. Given these 2 pixels, we can plot a point that corresponds to this simple image by using the first pixel as the x-axis coordinate and uses the second pixel as the y-axis coordinate. So for this image, we can put a dot at 1, 1 because both pixels are set to 1. Does that make sense? Yes. Likewise, if we had a second image with 2 pixels, then we could use these values, 1 and 0, to plot a point at 1, 0. Now, if we want to measure the distance between these 2 images, we simply measure the distance between these 2 points. Measuring the straight line between these 2 points is called the Euclidean distance, so it's not that big a deal. Note for larger images with more pixels, we just add more axes to our graph, 1 per pixel. For example, if we had 3 pixels, then we would add an axis for the third pixel, and then plot the points and measure the Euclidean distance between them. And when we have more pixels, we might not be able to draw a nice graph like this and plot the points, but we can still do the math to figure out the Euclidean distance. Okay, Alternatively, instead of measuring the distance between two images, we could calculate the similarity between them. One popular similarity metric is called the cosine similarity, and it simply consists of the cosine of the angle between the 2 points. There's a lot to be said about the cosine similarity, so check out the quest if you want to know more. Anyway, so just to dive in a little bit deeper, because we have a few extra seconds, we can measure the angle between the two images. And you can imagine if I had two identical images, they would overlap, and the cosine would be 1. Does that make sense? If the angle is 0, cosine equals 1. So that's the maximum. And if they're orthogonal to each other, like perpendicular, it's a 90-degree angle between the two, so they couldn't be any more different. And the cosine of that is 0, right? So that's the cosine similarity. We can use these angles. To be honest, it still kind of blows my mind that you can use an angle to calculate the similarity between two images, but you can. Anyway, so now that we know about this cosine similarity and Euclidean distance, we can talk about how we used them with our neural network. Specifically, because each image was converted into a column of numbers when it was input into the neural network, we can measure the Euclidean distances or cosine similarities between the input and all of the images used to train the neural network. Once I ran all 10,000 images that were not used for training through the neural network, check to see if they were correctly classified and calculated all of the distances and similarities, I drew histograms of the minimum Euclidean distances for the incorrectly and correctly classified images. So what that means is I got this testing data set, and I run them through, and some of those numbers are going to be correctly classified, and some of those numbers are going to be incorrectly classified. Regardless, I calculated in this graph the Euclidean distances between everything in the training data, and whatever was the smallest distance, I kept track of that, and then plotted these histograms for the correct and the incorrect. And what we see by eye, we can see that the images that were correctly classified tended to be closer to the images in the training data set because their distances were smaller. The smallest distance was smaller, getting closer to 0, right? When we calculated the mean distances of the correctly classified images and the incorrectly classified images, we see that on average, the distances from the inputs to an image in the training data set is smaller for the correctly classified images. And a t-test with a p-value way below 0.0005 confirms that this distance is significant. So it's not just random noise we're looking at, right? This is like a real thing with a small chance of being wrong about that, how real it is. So these results are consistent with my hypothesis that inputs that are closer to images in the training data set will result in better guesses from the neural network. Bam! I also drew histograms of the maximum cosine similarities for the incorrectly and correctly classified images. So this is the cosine similarity, basically the same data set. With the cosine similarity, the larger the value, the more similar the input images is to an image in the training data set. And by eye, we can see that the correctly classified images tended to have larger cosine similarities with the training data than the incorrectly classified ones. And when I calculated the means for the correct and incorrect classifications, we can see that on average, correct classifications are more similar to the images in the training data. And a t-test says that that's significant. So what this tells us is that not only are the results consistent with the hypothesis that a neural network can make better guesses for images that are closer or more similar to images in the training data, The results also tell us that we can use different metrics. Euclidean distance or the cosine similarity, and the conclusion remains the same. So we're somewhat robust to how we're measuring things. Robust, So that's a double man. And so, given that these results look promising, I'd like to see if I can apply them to chatbots based on transformers. For example, it's fairly common for a company to fine-tune a decoder-only transformer like ChatGPT to answer questions about their products. For example, a frequently asked question could be, how many slices of bread can I jam into my new toaster? Oh, this is such a rough draft. Anyways, it's a squatch ass, how many slices of bread can I jam into my new toaster? And the standard company approved answer could be, you can jam 2 slices of bread into the StatQuest or StatToast deluxe toaster. So they might take a pre-trained decoder-only model and then fine-tune it to provide the desired answer to this question. However, we can also create context-aware embeddings for the question. And then when we get a new question like this, can I jam 10 slices of bread into my toaster? We can create context-aware embeddings of the new question and then measure the distance between the embeddings for the 2 questions. And if the distance is too far, we could respond by saying, I don't understand. Can you please rephrase your question to something I've been trained to respond to? Or if the distance is small enough, we can the response, we can reply with the company approved answer. You can jam 2 slices of bread into your StatToast deluxe toaster. So that's the end. That was just a little fun thing I want to do, and I just think it's interesting that this is something I just played around with on my laptop. And the next step for me is obviously just to download an Encoder-Only Transformer and see if I can fine tune it based on certain phrases and see how that turned out. That's the next step for me. I'm pretty excited about that. It's just a little fun, and I'm glad you guys sat through it because I'm really excited about it. Okay, thank you guys very much. You guys are absolutely wonderful. If you have any questions, I will give you answers, the reliability of which is unknown. I'm worse than ChatGPT. And there's microphones you can use to ask questions. So just go up and ask a question. Or not, I can sing a song. Okay, I'll sing a song. Thank you for sitting around and listening to me jabbering about Transformers. Hooray! If that didn't inspire a few questions out there, I don't know what will. This is amazing. I feel like someone has to ask something. Come, someone. Here comes. We got it. Okay, good. A general rule, because in your life you'll have to explain things to people, right? And a general rule is if nobody has any questions, you blew it. because people don't like to admit that they didn't understand. So, and I do this all the time. It's like, yeah, okay. So it's nice to at least have a couple questions.
Hi, my name is Sharp. Thank you so much for your time here. My question is actually in relation. Can you turn on your mic? Okay, fine. Thank you. It's on. Just tap it a little bit.
There you go.
All right. Nice.
Yes, that's fine. Thank you again for your time. This question is actually in regards to your YouTube career, and tying in with the music a lot. So I think when your videos started appearing on YouTube, the only other people I remember being kind of popular around the time were probably like OChem Tutor. And so, my question is, what inspired you to throw in the bit with music? And could you also talk about your music upbringing?
Oh yeah, these are good questions. So why do I sing silly songs when I'm so bad at them? Why do I do that? I do it because it's fun. Making these videos is like a lot of work. Even this like rough draft that you saw still is like a lot of time and effort. I mean, you guys made presentations. It's not easy. At least for me, it's not easy. And so I do all this research. I do all, I make all these slides. I finally record all the audio. I edit it all down, blah, blah, blah. All this work. And I'm like, okay, let's party. And I like to party with a little silly song. And it's like a little celebration. It's the very last thing I do at the very end. And it's just, I don't know, it's fun. And some people hate them. And you could be one of them, and there's no problem with that. You can always skip the first 20, 30 seconds, 5 minutes. You don't have to watch all that stuff. You can just skip it. And I've got no problem with that. That's a legit way to watch my videos. But for a lot of people, I've been told that they like the silly songs because sometimes the topics are very intimidating. Like for me, um, like personally, I'm intimidated by a statistical concept called expected values. And even though I understand expected values, and I've actually made several videos about them, I just look at that E and I go, oh no. Every single time, years later, I still do that. And so I've been told that the silly songs at the beginning help people go, yeah, don't worry about it. We got you covered. This is going to be fun. And it helps people relax and they don't, like I get anxious when I see that E. But if someone starts strumming a ukulele, I'm like, okay, maybe it's not going to be so bad. I mean, look at that guy. He's got a ukulele. And so I do it. I do it for that reason as well. There's like it wasn't the inspiration was, hey, this is fun. But the reason why I've never stopped ever is that it's somewhat pedagogical in that people have told me that it helps them learn because it helps them calm down. I think a calmer person is going to learn better. So bam. Oh yeah, but people wanted to hear about my musical upbringing as well. So I grew up playing the cello. And the reason why I grew up playing the cello was I was very young at the time, and my parents had wanted me to play something, and they let my older brothers vote. And so for the next 15 years, I had to lug around this huge thing everywhere. I had to take it to school on a school bus. You know what a cello is? A cello is an instrument that standing from the ground is about this tall, about this wide. It's very fragile. It's made of wood. It's hollow. If you bang it around, it's going to break. So imagine giving a 7-year-old this massive thing and saying, take it to school on the school bus and don't break it. And not only that, I had my cello in one hand. I had a big plastic box full of all of my Suzuki music that I had to learn. And because I was 7 years old and only this tall, maybe even shorter, I had to bring a chair. Because playing the cello is a lot about playing the cello is sitting at a very specific angle, like super straight back, it's like posture is very important. So I'm on the school bus with a cello, a box of music, and a chair, and a backpack full of stuff, right? And I go to school and I'm careful with that. And then at the end of the day, I had to take a city bus, and I'm this tall and I'm lugging all this stuff around. And I get on the city bus and I go downtown to take my cello lesson. And I had to do that 15 years. It's so small and I love it. I can throw it in any bag. It's transports. No one even knows I have one half the time. I show up these things and I'm like, where's your ukulele? And I'm like, well, surprise, it's in my bag. I couldn't do that with a cello. If I showed up with a cello, I'd be like, oh yeah, you definitely have your cello. Yeah, so that's I rag on the cello. I actually love playing it. I had a successful cello career. I used to be a professional cello player. I love it. But I love the ukulele. So anyway, so that's the answer to both questions. That's the story.
So then, did your brothers not have the chance to vote for like a contra base or anything?
I'm sure. So the question is, could my brothers have also voted for the double bass, the contra bass, the big huge monster? And I'm sure if they knew it was an option, my life would have been even worse. Yeah. Yeah. Okay. Second question. Sorry.
Hi, Josh. My name is Stephanie. Thank you for the great neural network presentation. So, having learned about the basics of neural networks and the different flavors of neural network models, when I use ChatGPT, I kind of base my prompts on what I think the model was trained on. So, presumably using capital letters, or I try to not misspell words so that I can get the best response I can. And that reminded me about like what your presentation was in terms of having other words that are close to the training data. So my question is, how do you think knowing more about the foundations of these concepts can help with things like prompt engineering to help us maximize the usefulness of these tools in practice?
That's a good question. Yeah. So in this little thing right here, the whole idea behind this is to give us some sense of how far off my prompt is from what the thing is trained on. And I'm going to be honest. I'm not going to answer your question, but I'm going to talk. So let me go, right? So when I just learned this the other day. This is actually kind of funny to talk about how a lot of people think I was born knowing all this stuff. I just learned it, right? And so I'm all excited about things that I just learned. I don't know if you guys get excited about things you just learned, but I get really excited. I want to tell everybody, so I'm going to tell you. Okay, so when transformers are trained, they have this like foundational stage where they give it the entire Wikipedia, and all they're doing is they're doing next word prediction, and that's not really how ChatGPT is actually used, right? ChatGPT is used not necessarily. I mean, that's how it works. Is it predicts the next words, but the prompts are very different from what it's been trained on. Like the prompts before were the pizza came out of, and then it predicts the next word, right? But usually you don't write the pizza came out of as your prompt, right? You say, could you tell me, what do you bake a pizza in? And the answer should be oven, right? So there, what they call is a misalignment between how that foundational model was trained, just predict the next word, and how it's actually going to be used. And so that's a huge data set. That foundational training is like the entire internet. And so it's too big to really store in an efficient database, right? If I kept track of every little input phrase and put that in a database, it would be massive, and just calculating these distances would take years, right? And nobody wants to spend years waiting to decide if your prompt is similar or dissimilar. So what happens after that is they want to then align the transformer to the way it's actually going to be used. So then they start, instead of just having it predict the next word, they start doing what's called fine tuning, which is that you give it a real prompt, like, what do you make a pizza in, or how do you cook a pizza? And with a known real answer. And they kind of train it on that smaller, fine tune it on its smaller level. There's some fancy stuff they do after that. And I'm actually going to make some StatQuest videos on that fancy stuff called reinforcement learning with human feedback. I'm going to try to explain that in the next couple of months. But that fine tuning thing, what's nice is that data set is smaller. And so we can keep track of that in a data set. In a database. And we could calculate those distances between the input prompt, or whatever you say, and whatever we had in our fine-tuning data set. And then we could say, hey, you just did this prompt. I'm just giving you a heads up that prompt was 50% further away from the input than the average prompt, or something like that, right? Give you some sense of feedback. Nobody does that right now, but wouldn't that be nice? So, so this is where I'm trying to like work on this to see if there's something there. And that didn't answer your question in terms of like tips and advice, but it's something I'm thinking about. I guess that's all I'm saying. So, do you have something I can't answer?
Well, for what it's worth, I think your presentation actually did kind of answer my question because I always wondered about how I can apply what I'm learning and helping students here as well. But I guess your presentation put into words that what I was doing, what I was fine tuning my prompts
Yeah.
to be closer to what I thought the training data might look like, and I think that's what you demonstrated.
I convinced you that was worth your trouble.
Right.
Yes.
So it's based on something.
Yeah, that's right. So you weren't just wasting your time. Yeah, good. Hooray. So answer the question. Bam. Exactly. Oh, I have stickers. If anybody wants a sticker, come up and say hello. What just happened?
Rafa wants a sticker,
Well, don't be shy. I've got a sticker for you.
Take two, Rafa, two. Yeah.
That's Rafa.
Okay, next question.
Thank you for the great talk. I have a question about the application of the BERT model. So since it is very good at obtaining similarity between data, do you think if you might have any data that's not work but position independent, you can train it and make a model and maybe can we use it for the unsupervised clustering method? And if it can work, do you think it can work better than other like conventional methods such as like k-means clustering, something like that?
Yeah, so there's a book called Hands-on Large Language Model, written by my friend Jay Alomar and his friend Martin. I don't know his last name. Anyways, they have a great example that I then stole. Well, I borrowed because I attribute it to them, and I say you should buy their book. And every time I get a chance to, I say buy their book. They have a great example where they take 27,000 unlabeled documents, and they use BERT to cluster them, and then they combine that. They can extract keywords. They use BERT to then extract keywords from the documents, and then they use those keywords and they plug those into like a ChatGPT generative AI model to generate labels for each cluster. It's one of the coolest things ever because it's the kind of thing like that when I was, I used to work in a genetics lab and we were getting all this like genetics data about mice, genes, and things like that. If I could have done something like that based on like what the data says about what these genes are doing, it would have like made my life so awesome. And so I don't know if that answers your question either, but I think it did because I think I was referring to unsupervised method of clustering things. So yes, definitely. So you can either check that out in Jay's book or you can get my book, and I have the same example. But if you do that way, then you still have to get Jay's book because I would feel bad if you just got mine. And Jay's book's got a house and other things too. That's super cool. So you could just start with his book and skip mine, but that would make me sad. So you're in a tight spot. Yep. Okay, now you can ask a question.
First of all, thank you for your time. I
Yeah.
really appreciate the talk. I wanted to talk to you about more traditional machine learning methods because a lot of them are now using transformers, be it classification or vision, basic tasks in machine learning. Can you explain why, first of all, why are like a lot of people just brute forcing transformers into classical machine learning problems? And then would they use encoder-only, decoder-only, or the encoder-decoder architecture?
So, to be honest, I feel like in business and like actually trying to do data science, I would think that the encoder one is the more useful of the two. The generative stuff is nice for creating labels and little things like that, but that's most like icing on the cake. The meat is what is done by the encoder thing. Now, why are people doing that when they could use a decision tree or a random forest or something, or even a linear regression? That is because they've been swept up in the hype of all the cool thing, or it's all the shiny new stuff. And just so yesterday I did a little Q&A, and there was a friend of mine, a very new friend of mine. He has a podcast called, I don't know the name of it, but it's going to come out. So you can, if you follow me, I'm going to be on his podcast a week from yesterday. So this coming Thursday. And the whole point of the podcast is these guys, it's him and two friends of his that are hiring managers at companies, at tech companies. And the whole thing is talking about what people think they need to do for their job versus what these people know they need to do for their job. And because they're constantly finding a mismatch between what people think they need to do, so they're like figuring out how to use all these fancy models, but they really should just be learning how to do basic things because that's actually more practical. But people just get swept away and they feel like they don't do the latest, greatest, they're going to be left behind and become obsolete. And that could happen, but not right now. The old stuff has been with us a long time, it's still around. And it's still the meat and potatoes of most work. It should be, yeah.
Thank you.
Oh, hold on. It's called
Data Neighbor Podcast.
Data Neighbor Podcast. I need my old man glasses to read that. It's embarrassing to do in front of people, but I do it. Because otherwise, who knows what I would have said. Okay, next question.
Hi, Josh.
Hello.
I'm Jonathan.
Hey, Jonathan.
Thank you for this presentation, but also just for all the presentations you do. I have a background in math education, so I really appreciate it when you talk about all the time, what you put into these. I totally get it. I'm actually curious what your process is for making these presentations, what sort of tools you use. Like, how much of this is hand-drawn? How much of this is special fonts? How much of this is you use some other tool and paste it into a PowerPoint presentation?
Yeah.
Like that kind of stuff.
Oh, I can go on that. Watch out, people. I used to use PowerPoint. Now I use Keynote, which is free with this Apple Macintosh, so it's cheaper for the self-employed because it comes with a computer. I use pretty much all the default settings. The main font I use is just whatever it was, when I opened it up. The color palette is like whatever they have when I open it up. I do change a few things, like they've got this font, and I use that for kind of like fun stuff. And over time, I've started, mildly customizing things. But I'm gonna be honest with you, that's also a preset. And so is that. There's like enough presets. It's like they did a really good job designing it because they give you like enough presets that you can do enough variety, I think. But not so many that I get overwhelmed by choices. There's just enough good choices. There's a few good choices. So pretty much I'm just using the default settings for all of these things. One word of regret that I have is that I did not start doing things in dark mode a long, long, long time ago. You ever watch those 3 blue, 1 brown videos?
Yeah.
He's always done dark mode. I'm totally jealous. Why did I not do dark mode? I did it just because this was the default. Dark mode was not the default setting back when I started doing this, and now I've just got my head wrapped around, and I can't think in dark mode. I've just done this so long, everything seems backwards. If I've tried, I'm like, this is hard. But I love it so much. Like my book is written in Keynote. Nobody writes a book in Keynote. That's a presentation software, but I wrote it in Keynote. And all the tools I use are basically the free tools that come with the Mac. And my early videos were actually just recorded on the microphone built into the laptop. And some of those are my most popular videos ever. So it's not really about having like a fancy setup or fancy software. I'm just using the free stuff and I'm using the default settings.
What about Swatch?
And squash, yeah, squash I drew, but it just, yeah, it's all, this is like, you'll notice that squash doesn't have hands or feet. It's because I don't know how to draw. So I'm just like, what are we gonna do with that? Yeah, so I mean, I can show you. Hold on, I'll show you real quick. Let me exit this. Is this interesting to people to kind of see how I do this?
Yes.
Okay. Okay, hold on. Just give me a second. I'm gonna exit this. What is that? Now, I'm gonna share because USF has the easiest thing ever. Look at that. Okay, cool. Let me show you how I do this. Let me get the old man glasses. Okay, so this thing has a shape thing, right? So I don't know why this is a top secret tool. They got these basic shapes, but I like this tool. This is the one I use for everything. Get rid of this. But say like we want to draw squash. Go off the screen because that's where his hands are. I don't know what this is. This is a disaster. I don't know what that is. And so then what you do, you're like, well, let's make this cool looking. And look at these nice presets. We do that. And then we go like, oh, that I can't see that. That's too subtle. Let's crank that up. Ooh, that looks better. And now we'll give it some nice little fill. And that's the fill, and that's too bright. So what we do is we come down here to the opacity. We put that to 20. And so now we've got this like weird pink thing. And I don't know what that is. Maybe that's a crazy hat.
The Gamma Monster.
Oh, you guys want to see the Gamma Monster? Yeah. I'll draw the Gamma Monster for you. I created this new thing called the Gamma Monster. So we use my favorite tool. We do this, 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 and then we go back to the fuzzy line. We give it a bigger thing, and we give it make it gray. And then we make the fill light gray, and we make it, that's good enough. Okay, but this is cool. But I want it to look like a gamma distribution. And there it is, look at that. That's very good. It's kind of gamma-y. And now, that's pretty good. And now what we do is we gotta give them, gamma monsters kind of like heat pretty intense. We kind of look grumpy. Let's get this line and get rid of that, get a arrow. Did that already. Gray. So that's kind of, he's a serious dude. And then what we do is we make a little eyeball. Look at that fuzzy border. This. Come on, let's do this. This is the Gamma Monster. And so I don't know. I mean, yeah. So I just draw these things, but obviously I'm not very good, right? That's not Picasso, is it? It is. Anyways, yeah, good enough. So yes, the overall process is I have to learn this stuff, and I'm learning it right before I make the video, right? And my process of teaching is same process of learning, right? I have to come up with these little examples, little drawings, because I'm very visual, and a lot of people are like, hey, look at this fancy equation. I go, but if I can draw a picture, what's nice is a lot of math does have a geometric representation.
Right.
And that's like any mathematician would have a heart attack when I'd say that, because they're like, the whole point of the equation is to abstract beyond that simple geometric representation, and the abstraction allows it to be used in all these other settings. I'm like, but no, that's too complicated for me. And so I just draw a picture, and then what I do is I base it off that picture and sort of build on that.
Yeah, it helps us all learn.
Yeah.
We're all visual.
Yeah. So But it is a slow process. I'm good at the gamma monster, but the other stuff takes a long time.
Thank you.
Thank
I
you.
appreciate it.
Yeah, that was fun.
Hello, Joes. My name is Ellen. Thank you for your presentation. I must say, we don't ask questions. I think you explained things very well in the beginning.
Wow,
Hence,
that's
we don't
all.
have that question. I have a questions regarding, especially your second talk on interpretability of like neural network and AI. It's also something that like I think we've been teaching a lot about this. So you know that neural network could be like complex as the problem group. I think from the business or real world perspective, how I've seen things like companies or like corporates, they want a model that is works minimizing the error, etc. But from like a statistic academia perspective, we want a model that's interpreted. It needed to interpret. Uh, I realized the more the neural networks model grow, the more features, the more this noises data we have, it's difficult to interpret things. How do you justify the balance between like I want to have a model that like works, but in the same time it's interpretable? It's in the end of the day when we solve cases, we care more about like the result itself. I want to minimize the risk of the losses. I don't want to misclassify if I predict some I don't know, cell cancer. So it's always like if I want to be able to interpret it, I end up maybe losing a better model because I have to reduce this complexity. What's your thoughts?
Yeah. So
Yeah.
as always, I don't know if this is actually an answer to your question, but I will ramble.
Yeah.
So some fields like banking and finance, they're not even allowed to use these neural networks because they're black boxes and they can't make decisions on whether or not someone gets a loan based on a black box. They have to be able to explain the rationale behind their decision, right? And so in some places, the fancy models like these aren't even can't even use them, right? And so that's something to think about, right? Because if you want to get into finance, then you get really excited about models like XGBoost and like GBM and these other like tree-based models, because tree-based models are inherently interpretable. And so I spoke at a bank a couple of months ago, and they were all, it's like they learned about this, and I'm like, well, that's very interesting. We'd rather learn about this other stuff. So there's not just interest, but there's federal regulations demanding that the model be interpretable. And so that's something to think about with respect to neural networks, right? Because they ultimately end up being a black box. And then I forgot the other part of your question.
Or would that be like a threshold where you can like justify still building, I don't know, the model that's like complex enough to solve the problem, but like interpretable enough?
Yeah. And that's something that I like about is, at the end of the first talk, when I was showing how we could use these embedding values as inputs to a legislative regression. How interpretable is that? I don't necessarily know. But I think it's better than using a neural network. We at least have some sense of what's going on. And if we do based on the training data, and like again, if we can keep let's not look at this guy, let's look at this. If we can keep track of our inputs that we fine-tuned it on, we can, like we keep track of like how far things are from it, we can learn how to have faith and more confidence based on that. We can also what's it gonna do? I don't know, there's like a bootstrapping method where you can or there's these things called SHAP values. Are you familiar with SHAP?
SHAP line.
Yeah.
Yeah, so that's something to look into as well. I know they apply to neural networks as well, and that might give you some insight as well. I don't think I gave you a good answer, but
And a fan request would be great to have XAI, explainable AI like this in your videos. Like I think it's really interesting. For the upcoming videos.
I'll keep that in mind. Thank you. That's great.
Hey Josh, how's it going?
It's going great. Is the mic on?
Let me check.
Visual will help out. Doesn't sound like it.
Okay.
We have a
I can just project my voice. That's totally fine.
And then you can repeat the question.
I can repeat the question. I don't know if that has a battery. That sounds good. All right.
Some great technical difficulties. All right. Hey Josh, how's it
Hey,
going?
going well. I just gave a talk. I'm really excited.
I'm doing good myself.
Awesome.
I appreciate it.
Yeah.
Yeah, I just want to first of all start by saying that you've been a really indispensable part to my education. I wouldn't have been able to go through undergrad, even grad school, without your videos. Gave me a lot of intuition regarding different statistical concepts and just really understanding transformers. I've finished a lot of your videos, and so from the bottom of my heart, thank you very much for all that you do. I know that being a creator often feels a little bit thankless, and there's a lot of work that goes behind it. And you have a pedagogy and you have a lot of things that you need to do. So seriously, I really appreciate everything that you do for the community in this space.
You're gonna make me blush.
Anyway, let me go to the part of my question.
Okay.
So the first part of it is, I know that as part of your pedagogy, you have this repeated, emphatic use of the word ban. So
Yes.
I am curious about where it did come from. Was it a daydream that occurred to you, or how did it come about?
So a couple of things. So when I first started making these videos, they weren't videos at all. They were just PowerPoint presentations that I used to give my coworkers and say, "Hey guys, I'm going to teach you statistics today," and they'd be like, "Oh," and they hated statistics and they didn't want to pay attention at all. And so, and oftentimes my friend Dom, he'd sit in the back and he'd fall asleep, and I'd look at him and doing that. And so I decided I had to make statistics more exciting. It wasn't enough to say, "Hey, check out this equation. Isn't that cool?" Right? I had to be like, "Bam!" And so so BAM was a way to make things exciting. But BAM actually came from an old cooking show. There used to be a show called Emerald. And Emerald was this Louisiana, New Orleans chef. And he cooked the way I wanted to teach statistics. He had a band, a live band. That's my dream. To have like a warm-up band that gets everyone going. And they get the t-shirt guns, they pop them out in the audience. And everyone's like, yes, StatQuest. And so that's the dream. And then while he's cooking, he's just like, he's adding seasoning, but he's Cajun or whatever. So he's adding like spices. And so when he adds the spice, he goes, "Bam!" And I was like, "Oh, statistics is spicy too, right?" Oh, maybe it's not, but I'm still thinking, right? So that's where it came from. But there's the thing: I only do the three, right? I only do three. So the question is that I just asked myself. Let me repeat it. Why are there only three BAMs? BAM, double BAM, and triple BAM. I was making a video on logistic regression. And I was like, "Oh, that's a BAM. That's a BAM. We could talk about odds. If we're going to talk about logistic regression, we're going to talk about odds. BAM. We got to talk about log odds. BAM. We got to talk about log odds ratios. Triple BAM. Now we can talk about the exponential, the sigmoid function. That's a BAM. We got to talk about all these things." And I kept going. And I had a PowerPoint or keynote presentation that had like 800 slides, and it had like 10 BAMs, and I was like, "This is going to take like 4 hours to do. Maybe what I need to do is just stick with 3 BAMs per thing." I broke it up into ultimately like 8 videos, and each one had 3 BAMs, and I was like, "Oh, I like that because it allows me to focus on specific topics without going, and just overwhelming people." Which is, I don't know if I do this myself. I'm not saying I'm not guilty of this, but I used to go to these genetics seminars all the time where some guy would like try to convey his entire life work in 45 minutes. And I swear, after like 20 minutes, my head would go, "I can't do it anymore.